Okay, maybe it's a good time to start. Welcome everyone. What the main organizers might like to come and say some things to begin? Grant or?
Sure. So welcome everybody to the UV meets the IR Zoom conference here in virtual space hosted by KITP. We're very glad you all could make it. Thanks very much to our wonderful list of speakers, and we hope this conference is a way to get all of the different communities interested in this field talking with each other. Amplitudes, phenomenologists, swampland people, and all the rest. So thanks. Isabel?
I think that's about right. I think we can start. You think feel free to take it from here.
Okay, so great. Okay, so let's start. So we're happy to have John Marshall from Oxford, and he'll begin with the first talk. And it's, if this is the best of all possible world, what then are the others? So please take away.
Well, thank you very much. Thank you to the organizers and to KITP for organizing this. Seems like a very stimulating mini conference. Just a pity we can't all be physically there, but at least the advantage is the world can see the talks recorded. So what I want to tell you about is a set of works that I've mainly done with my PhD student. So let me just do the thing. So if you can see this okay. This is my student, Rudin Petrosian-Brun. Here he is. These are two papers, QCD flavor in the Determinant swampland, already out in the archive, and then a long follow-up, and then probably some more papers as well on electroweak symmetry breaking and the Determinant swampland. In fact, I'll probably mainly talk about the second one. There's a few other things I'll speak about going along. I want to emphasize that this is a talk as a phenomenologist beyond the standard model theorist. I'm not a string theorist, but I'm going to use various of the current swampland string conjectures and see what mileage we can make out of it. So let's go on. So the swampland program, I'm sure.
Sorry.
Yep.
The slide isn't moving actually.
Huh.
And the slide is still stuck at the first page.
How if I just do this? Can you see it now? Can you see that first page? Can you see the second page? Hello?
Yes.
Yes, now we can see.
Good. You can see. I don't know. Okay, it somehow doesn't work. Maybe play then for some reason. All right, let's do this then. So here's Rudin, and so this is going to be about using the swampland. Of course, swampland program in its modern incarnation is due to Baffer and his many co-workers, dominantly. So the idea is basically that not all otherwise consistent quantum effective field theories can be embedded in a theory, including quantum gravity. And sometimes actually you might want to impose a strict version, which cannot be embedded in string theory in the ultraviolet. So we now have good evidence, though not proofs most of the time, that there is a difference between the swampland of apparently consistent effective quantum field theories and the true landscape of consistent quantum field theories when you include gravity. And of course, it's a very good thing if we have restrictions on the possible low energy effective field theories we can have. We used to believe renormalizability was a key criteria. Now we think differently. It'd be marvelous if we have these new restrictions. So there's a huge, ever-growing list, interconnected list, I want to emphasize, of swampland criteria. Most of these are conjectures. A few have partial proofs, and they're often either sort of partially formulated or with unknown order-one constants appearing. And of course, they have, as I said, various levels of support, and some are more controversial than others. There are many important open questions, many important theoretical questions, but here I want to focus on this phenomenological issue, which is what impact could or does the swampland program have on our understanding of the standard model, if any. And of course, there's some previous works thinking about these directions, but I'm going to go off on a rather different track from these previous works. So the first thing we can say is the best supported and oldest swampland conjecture is probably the fact that global symmetries are not exact in gravitational theories. And of course, this goes back all the way to Wheeler and Zaldovich and Hawking and various others. And of course, in recent years, it's been extended by the weak gravity conjecture, which stops us realizing a global symmetry, exact global symmetry. This is zero coupling limit of gauge theory. And there's been partial proofs in various circumstances, like in ADS-CFT by Harlow and Aguri. Already, this no global symmetry statement really tells us something quite remarkable about standard model parameters, if you think about it. The standard model has the following non-anomalous global flavor symmetry, broken only by the Yukawa. So SU3 acting on the left-handed quarks, SU3 up, SU3 down, SU3 left, right, SU3 leptons, and times some further thing in the neutrino set we don't know exactly. So the claim is that embedding in quantum gravity stops us taking two or more Yukawa couplings of equally charged matter fields equal. That's really an extraordinary statement if you really think about it. It's quantum gravity that stops us taking this limit and having enhanced exact global flavor symmetry. This, of course, is consistent with observations. We don't observe any of the equally charged matter fields to have equal Yukawa couplings. But if only exact equality is forbidden, then in fact this is even though it's conceptually interesting, it's not a very useful statement. So I want to argue first, and this is based on work I did this year with Tristan Dowse, Arthur Hebecker, Sascha Leinhardt at the University of Heidelberg, is in fact, and it follows on from earlier paper of Fischer and Sasarawat, that in fact the full swampland global symmetry conjecture likely carves out a larger portion of standard model parameter space rather than just this measure zero set. Okay, so let me first tell you what the argument of Fischer and Sasarawat was. Well, they had a thermal argument involving black holes. They declare that in a thermal bath at some temperature T less than the UV cutoff, the rate of global symmetry violations to satisfy what they call the local rate bound. This is a statement that the effective field theory, suitably defined, has a rate of global symmetry violation which is strictly bigger than the rate due to black holes. And what's happening with the black holes? Well, black holes are forming by thermal fluctuations. So here I have a bunch of, say, baryons with baryon number n, go to a black hole Hawking evaporates, and of course I, statistically speaking, violate baryon number in this way, this statement. And their argument of Fischer and Sasarawat, using this sort of thermal argument, places a lower bound on the size of global symmetry violation in the effective field theory. So this argument is a very stimulating argument, but it has mysterious aspects, at least to me. So I want to go on to, let's see if there's a different way of making a lower bound and what the strength of global symmetry violation is. And this is, in fact, our paper with Tristan, Arthur, and Sascha, which is a weak gravity conjecture based argument for a particular subclass, or a very common subclass of global symmetries, which is gauge-derived global symmetries. So here we can use the zero form version of the weak gravity conjecture and the completeness hypothesis as well. And that means if you have a world line of a particle with some global charge going along, there must exist some quote-unquote instanton that terminates this world line. And when you consider this process and sum over this in the functional integral, what you find is this leads to a global symmetry violating operator in the effective field theory, which is some local operator here, phi of x, which is carrying, in this case, let's say, global symmetry quantum number 1, with coefficient e to the minus si, where si is the instanton action. And in fact, you can go further, and you can use a combination together of the electric and magnetic forms of the zero form weak gravity conjecture, and instantly these bound instanton actions, and you find there's a bound on the size of this instanton coefficient, so e to the minus si is exponential of some order 1 coefficient, m Planck squared over lambda squared, where in fact you learn that lambda squared, by actually earlier work of other people, including Arthur, that this is related to a string tension. So in fact it's not a zero measure space. There's actually a lower bound on the strength of global symmetry violation we have to have. We can't send this global symmetry violation below this bound here. And in fact, this is exactly the same form as that derived by Fischer and Sasarawat by a completely different argument, this thermal argument. And I can go on in much more detail in the discussion if you wanted to about what actually our arguments are on this paper, but I just wanted to tell you there is this bound. So we carve out some small, but not zero part of measure zero part of parameter space. So this is better than before, but unless we can argue that this UV cutoff related to a string tension is very close to M Planck, this lower bound on global symmetry violation still only forbids an exponentially tiny region of the standard model parameter space. So the question I want to ask here in this talk mainly, and this is based on my work with Rudin, is can we do better than this? So I'm going to use a bunch of recent swampland criteria, in particular related to de Sitter space. So one of the most striking, in fact, one of the strongest of all the conjectures is the refined swampland de Sitter conjecture for a potential of all the scalar fields in the theory, V of phi. It says that either the absolute value of the derivative in field space of the potential has a strict lower bound, which is some order 1 coefficient, the size of the potential over m Planck, or if this is violated, the second condition, which is the second derivative around that point, has to be smaller than some particular value set by the size of the potential. So this condition here has the very interesting, striking consequence that says that metastable de Sitter vacua are in the swampland. All right. So even though you think you could write down some normal effective field theory, in fact, that has a metastable de Sitter space as a vacuum state, or at least as a metastable vacuum state. In fact, we can't do it. It also forbids parts of field space that are too flat, at least for positive potentials. There's actually a second condition. And why is this not going on to the next one? The second condition. Can you see this? Can you see this next one? Next page, Transplantian censorship.
Yes.
Good, thank you. So there's another condition, which is the Transplantian censorship conjecture. This is recent due to Bedroyer and Vaffer, 2019. Well, this is a weaker global condition than the swampland de Sitter conjecture. The swampland de Sitter conjecture is a remarkably strong local condition in field space on the potential. And in fact, of course, its intention, you might think, unless you believe things like quintessence or maybe thermal dark energy, as Susha later on in this conference will talk about, its intention would observe cosmic acceleration. All right, and we can talk about other possibilities there. But there's this weaker condition, which is more of a global condition on the potential, which is this Transplantian censorship conjecture. In words, it says sub-Planckian quantum fluctuation should remain quantum and never become larger than the Hubble horizon, and therefore freezing in and becoming classical. Right. So there's a limited amount of inflation we're ever allowed to have to expand sub-Planckian quantum fluctuations up to classical scales, large scales. So this also forbids long-lived, and long-lived is the important caveat here, long-lived metastable de Sitter states. They're forbidden if they have lifetime which is bigger than the 1 over the apparent the appropriate Hubble parameter, so just the Hubble parameter related in a normal way to whatever the maximum energy density is, times this log factor. So if you have a lifetime, you have a metastable de Sitter state that has a lifetime which is longer than this, then they're forbidden. Short-lived metastable de Sitter states are okay. And I should point out that for our current measured value of the Hubble parameter, in fact, this allows the lifetime of our current universe to be about 140 Hubble times, because its log factor turns out to be 140 for that. So it's perfectly consistent with having a small cosmological constant now, but forbids very, very long-lived, appropriately measured in terms of this Hubble parameter, de Sitter space. And in fact, I am going to dominantly use that second criterion, and I emphasize this is a weaker criteria, at least for sub-Planckian field ranges. This is a weaker criteria than the swampland de Sitter conjecture. So I'm going to make the claim in this talk that plausibly either the swampland de Sitter conjecture, or here I'll show you the arguments for the Transplantian censorship conjecture, limits the flavor structure of quarks and maybe even sheds new light on the hierarchy problem. And this is these two papers was written. Okay, so what are the arguments? So here's a teaser preview, just to keep you interested so you don't fall asleep. Here's a teaser preview of what I'm going to explain in this talk. So on the x-axis here is the Higgs mass square parameter varying from minus m Planck squared through 0 up to plus m Planck squared. And I'm going to claim this red region here is excluded by a calculation I'll show you because of the existence of metastable states in this region. I'm going to show you, I'm going to argue that the standard model, in fact, is not ruled out by the existence of metastable states. So where the standard model sits with slightly negative Higgs mass square parameter, giving the observed electroweak Vev, and then possibly, depending on some unknown properties of pure SU3 QCD, it's possible that also there's large negative values more negative than minus 30 TeV squared, are also forbidden. So in fact, there's just a narrow range, we might be able to argue, where the Higgs mass square parameter can live. I should say there's another yellow region here, which our calculational techniques at the moment break down. We have to do a revised calculation, and we're thinking about that at the moment. But let me explain. What I'm going to explain in this talk is I'm going to explain why is the standard model okay, and then I'm going to explain this region on the right for positive mass square parameter. And if I have time, maybe in questions, I can explain our logic for this region here for negative mass covariance. So that's the teaser of what we're going to do. So first of all, everything is going to be here about metastable states of standard model or of QCD. So let me explain the ideas. So there's a very well-known old story, which is metastable states of QCD with light quarks, due to Witten and Kreutz and Smilger and lots of other people, Schiffman. So consider SU3 QCD with n light quarks. So this theory is confining, chiral symmetry breaking occurs. So SUN left cross SUN right goes to SUN vector. So low energy physics is determined by the pseudo-Neber-Goldstone boson chiral Lagrangian system. So here is our kinetic term, and here is the leading mass term. So this is the thing that will generate the potential. Okay, and here I've written the pseudo-Neber-Goldstone bosons in this usual Callan-Common-Wesson-Mino form, this exponential form. Right, so TA here are the generators of SUN. Okay. So what are the parameters of this theory? Well, there's the theta bar angle, which is the topological angle, and there's also the quark masses, which I'm arranging in this ordering where M1 is the heaviest and Mn is the lightest. And in fact, there's only really n parameters here because I can always scale out an overall scale out of the thing. I only care about whether there's critical points or not critical points, and therefore it's only the quark mass ratios that come in. So in fact, there's n dimensionless real parameters, the theta bar angle, and the n minus 1 quark mass ratios. So it turns out you can show that all space-time independent extrema of this chiral potential are of the form, this sigma matrix is some overall phase which I extract, UTI theta bar over n, and then a set of diagonal phases. Right? This is an n by n matrix with diagonal phases. Okay. Well, if you substitute that into the previous mass term, the chiral Lagrangian, you find this is the leading order potential. So this is the potential that determines the critical points. It's a sum of terms where quark masses times causes of these phases comes in. And here, I just want to remind you that these phases plus this theta bar over n times f pi is just a renaming of the VEVs of the Cartan subalgebra pion directions. Okay, and there's also a constraint to have the conventional meaning of what I mean by theta bar, because I factored out this factor here. I have the constraint that the sum of phi 1 through phi m plus theta bar is equal 0 mod 2 pi. Right, that's just a definition of what I'm meaning by theta bar here. Okay, so this is the system. So you can straightforwardly study the critical points as a function of the quark mass ratios and of the topological angle. So let me tell you what the story is there. So a particularly simple case occurs if all the quark masses are equal. Right, in that case, you can show critical points force all these angles to be equal. They're all equal to 2 pi n for n some integer minus theta bar on capital N for all I. And moreover, the Hessian matrix around these critical points is positive definite. That means I have a local minimum, right? If this condition is satisfied, so little n, this integer, is between minus capital N on 4. I remember capital N is the number of light quarks I have my theory, plus theta bar on 2 pi, and then this other condition on the right-hand side. And so you can see that if I have n capital N greater than 2, there's an integer here that satisfies this condition. So for n greater than 2, metastable states definitely exist for some theta bar in QCD. So let me show you what they look like. So this is the case. This is a plot of the branches of the critical points. This was done by Smilger and other people, also Dubosky and Gorbenko. So this is 3 equal quark masses. So equal masses, and so the only parameter which controls the physics here is theta bar. And what you see is there are these red branches. With this lower red branch here, this is the ground state, but then it continues on and becomes a metastable local minimum. Right, and similarly, here's a branch of a ground state, and then as it occurs up here, it also becomes a metastable local minimum. And here are saddle points here, and these black curves are local minima of the situation. So what you see between here and here, and between here and here, basically pi on 2 and 3 pi on 2, and then of course all the periodic translations of that. In fact, you have metastable states in 3 light flavor QCD, right? At least for sufficiently large theta bar in this range. Okay, that's quite interesting. So let me go back. It's an important fact that in fact these states are almost everywhere very long-lived. So as long as you're away from the boundary of the metastable region, that means I'm away from where these red curves go over to being black curves. So this is a transition from being local minima, where it meets a saddle point and becomes a local maximum. So as long as I'm away from that region there, so as long as I'm close to this crossing point, and in fact not all that close, then the lifetime, as you can compute by Callan-Coleman or Coleman-DeLucia, depending whether gravity is important or not, is very long. So in fact, it goes like lambda QCD to the fourth, the decay rate per unit volume, and then some factor which goes like f pi to the fourth, the overall quark mass, which of course I could take tiny if I wanted to, this mass parameter that appears in the Lagrangian, and then this dimensionless difference between the crossing point, which occurs at pi. And so this value d is surprisingly large. It turns out, due to numerical calculations, to be 4 times 10 to the 3. So very, very easily, all right, you get this vacuum, this metastable state, to be extremely long-lived, much longer lived than Hubble time. All right? And we're going to find similar phenomena later on, so that's an important fact. Okay, well, that was for equal mass quarks. How about when you don't have equal mass quarks? Well, let's do 4 quarks, and let's put them in 2 equal mass groups. So then I have 2 parameters which control the physics. I have theta bar on the x-axis, and then I have the ratio of the lighter quarks to the heavier quarks on the y-axis. And now you see roughly half the parameter space has metastable states. What I want you to notice is as I make this mass ratio, as I make the mass ratio larger and larger, so closer to 1, right, closer to 1, more theta bar has metastable states. On the other hand, if I take the mass ratio very small, it's only a small region of theta that has metastable states. So that's the case for 4 quarks, one particular case for 4 quarks. What else can we do? Well, we can go. So what we argue, and I'm going to go into more detail later on, is we argue that all the regions of parameter space with metastable states are plausibly excluded by, depending on what your argumentation is, either the swampland de Sitter conjecture or the Transplant insensitive conjecture, from descending from a theory with gravity. So the first thing to say is, what about the observed standard model parameter values, 3 light quark masses and theta bar equals 0? Well, here is a plot of as a function of M3 over M1. So this is lightest quark versus, so that strange, up quark versus strange quark here. And here is the other parameter here, which is this is down quark over strange quark mass. And the standard model is this little red dot. Okay, so this is the standard model. In fact, it's free of metastable states for any value of theta bar. All right. On the other hand, if it had been in this green region here, then it would have been forbidden for large values of theta bar, or if in these dark regions, it would have been forbidden even for values of theta bar that are getting smaller. So the observed standard model is in a region of parameter space with no metastable states. Okay, and so it's not constrained by at least these Transplant censorship or the swampland de Sitter conjecture criteria. Okay, so that's that. So in fact, the condition of theory does not have metastable states for any value of theta bar in an n-like quark theory is in fact this condition here. 1 over the mass of the lightest quark is bigger than the sum of the 1 over the masses of all the other quarks. All right, and this is satisfied by the standard model because 1 over m up famously is bigger than 1 over m down plus 1 over m strange. But I want to emphasize that if we had had 5 or more light quarks with not very large mass ratios, then definitely have metastable states even at theta bar equals 0 in the standard model. So in fact, as you bring more quarks down below 4 pi f pi, all right, in the standard model, in fact, you would start generating metastable states. Okay. So this is interesting. It's an interesting fact that we only have 3 light quarks in our world and not 4 or 5. Incidentally, so this is a plot just of what happens, for instance, when you have 6 quarks and 2 equal mass groups. Again, you have metastable states to show you what happens. And you see, in general, the critical points of a theory like Q steam, this very simple theory, in fact, the Lagrangian are very rich. Okay, so that's that. Well, okay, so that's interesting. Incidentally, one thing I want you to notice is it didn't like mass ratios going to 1. That was the region that was forbidden. right? It's when you have completely equal quarks is when equal masses, that's the thing where you most easily have metastable states. And of course, that's the global symmetry enhanced point. And we'll see, in fact, there's lots of examples of that. The Transplant censorship or the swampland conjecture carves out regions that surround the global symmetry enhanced points. And later on, we'll see another example. Okay. So let's turn to a different limit to the standard model. And this is, now let's think about varying the Higgs mass square parameter. So I'm, first of all, because the arguments are sort of straightforward, complicated but straightforward in a way, calculable, let's consider the Higgs mass square parameter being large and positive. Right? So naively, this implies the electric wave is zero. So let's see what happens in this theory. So now, for the sake of argument here, I'm going to keep the standard model Yukawa couplings fixed, and for the moment, I'm going to ignore them, right? So I'm just going to ignore the standard model Yukawa couplings. And of course, if this Higgs mass parameter is very large, I can integrate out the Higgs, and I'm just left with a low energy theory, which just consists of SU3 cross SU2 cross U1 gauge fields with 3 generations of massless quarks and massless leptons. And again, no Higgs degree of freedom. So what is that theory? What's the state structure of that theory? So lattice studies indicate that this QCD theory still confines and breaks quark chiral symmetry SU6 cross SU6 down to SU6. And so here are the spontaneously broken directions, and here is the surviving unbroken vector subgroup. Right? So naively, this would if there was nothing else going on, this would be 35 exact Nambu-Gaussian bosons. But something else is going on, which is in fact we've gauged some number of generators. We've gauged these 4 generators because we've gauged this SU2 cross U1 subgroup of the entire possible flavor group of the situation. And the VEV we get, this chiral condensate VEV, in fact breaks electroweak symmetry, and 3 of the Nambu-Gaussian bosons, these 3 in this region here, are eaten. Okay. So now this fact we've gauged part of the group explicitly breaks the symmetry and gives masses and a potential to 16 of the super Nambu-Gaussian bosons. So in fact, this entire region here, this crosshatch region, the Nambu-Gaussian bosons that live in that region get a mass and get a non-trivial potential. And so let me just go on. So what we need to do is calculate the full potential function here, including the other branches. And what we'll find, and what we do find after a long calculation, is in fact there are metastable states here. All right. Sorry, on this potential, not metastable states here. For this part of parameter space, when we have large positive Higgs mass square parameter, we find that the potential of these pseudo-Nambu-Gaussian pion-like states indeed leads to metastable states. All right. Well, it's a rather complicated calculation. You can go through it. It's gauging. It's computing the one loop effective potential, etc., etc. In fact, it's an exceedingly rich and complicated system when you do this 3-generation case. There's a much simpler case which demonstrates the physics, which is just 2 generations. So 2 generations, everything becomes SU much simpler. It's SU4 cross SU4 down to SU4. Now there are 6 Nambu-Gaussian bosons that get a non-trivial potential. And in fact, using unbroken SU2 flavor symmetry, I can, remember I've turned off the Yukawa couplings so far, I can orient those 6 directions all into 3 directions. And so that's what we do here. So explicitly, here's what the potential looks like. It's some factor out here, which goes like alpha of SU2, alpha of U1 hypercharge, F to the 4th, F pi to the 4th, and then this sum of these 2 causes squared, where inside the cosine function, there are these combinations of these pion directions. So what you need to notice is this vanishes if either SU2 weak or U1 hypercharge coupling goes to 0. And all I've done, I've rotated axes just to depend on 3 field directions. So here I can plot this non-trivial function. So this is what it looks like as a slice. This is a 2-generation case density plot. And at the center of these blue regions, there is a minimum. All right? So there's a rich structure of minimum. I can do another plot in this space, which I can cut through the plane, the horizontal plane. And so here it is. Here are the various minima. So it turns out these minima are physically distinct. They have different values of the pion VEVs. They're deep as well. They're set by actually alpha prime times F pi to the 4th. That's a sort of difference in vacuum energies and the barriers between them. But they're degenerate. These are all exactly degenerate at the moment. And the reason they're degenerate is that so far we've neglected the effect of the Yukawa terms. If you turn on the Yukawa terms, what do you find? Well, if you turn in Yukawa terms, well, where do Yukawa terms come in? Well, we've integrated out this heavy Higgs doublet. But of course, when you integrate it out, you generate these 4 fermion interactions suppressed by 1 over m Higgs squared. And this generates new terms in the effective chiral Lagrangian. And here's an example of the term you get down at the bottom. So you can calculate the effect of this. And what you find is, for instance, and even if you turn on just one entry, like just the analog of the top Yukawa in this thing, let's imagine we're doing the heaviest 2 generations here. This splits the degeneracy of the subset. So now what you find is these central ones are deeper and these other ones, this line just above, are slightly higher in vacuum energy. So now you get a splitting between the vacuum energies. So now these ones here are metastable states compared to the true ground state of the system. Okay, so that's very interesting. So there's an interesting difference with the previous case when we were just thinking about, well, what are the constraints in Yukawa couplings? So now the situation is before we turn Yukawa couplings, we already have distinct deep minima due to the gauge interactions, but they just happen to be degenerate. Now, turning in Yukawa coupling splits them from each other, and we get these metastable states relative to the true ground state. Previously, in a previous argument when I was doing the flavor structure, Yukawas had to do 2 things at once. They had to both generate the minima and split them. All right. Now they only split them. Okay, that means we don't care about ratios of Yukawas anymore as long as they're not at the global symmetry enhanced point. So that means any ratio of Yukawas, as long as they're not at a global symmetry enhanced point, will lead to non-degenerate minima, metastable states. Okay, so that's an interesting thing. So what do these metastable states look like? Well, they're split from the ground state by an amount which goes like the they're split from the ground state which looks like the size of the Yukawa coupling squared. So the biggest splitting will be to the top Yukawa coupling squared, f pi to the 6 over m Higgs squared. Now, this is a tiny splitting, at least when m Higgs squared gets very large. But what I want to point out is even when m Higgs squared goes up to m Planck squared, this splitting is much bigger than the observed size of the cosmological constant. Okay, and that's going to be important. Moreover, there's a second thing. Just like the previous case, these are extremely long-lived states. In fact, you can estimate their tunneling lifetime to the ground state, and it turns out to be alpha squared, alpha prime squared, m Higgs over lambda QCD to the 6th, where this coefficient C is somewhere between 10 to the 2 and 10 to the 3. Actually, we need a more accurate numerical calculation to fully pin this down. You get to do that. So once m Higgs becomes, let's say, bigger than about a GeV, this lifetime is exceedingly long. In fact, it easily exceeds the present Hubble time. Okay, so these states in this whole region of large positive mass squared are very long-lived states. Okay, but remember, all right, if you go back, that the Transplant censorship conjecture says that these metastable states are forbidden if the lifetime exceeds this maximum lifetime, which is 1 over the Hubble parameter, so the Hubble time up to this logarithmic correction. And if I put those in for the splittings we have here, and I take it for the, say, the top Yukawa case, what I find is this formula here, but this lifetime is very short compared to this tunneling lifetime we calculated before. So that means that these states are excluded, all right, by the Transplantian censorship conjecture. So this part of parameter space, so say it carefully, this constraint is hugely exceeded by the calculated decay rate. So the parameter space that gives rise to these metastable de Sitter states is excluded by Transplantian censorship. Okay, so that excludes a very large part. So here is the picture. Here's just the positive part of the sort of teaser figure I gave you before. So our claim is this whole region here up from about 1 GeV, and we don't know exactly where the boundary is for numerical reasons, but all the way up to m Planck is excluded. So these are the metastable states, and I want to emphasize that all these splittings here are reliably calculated from the IR theory, right? So we know exactly what these splittings are. That's a good calculation. And this region here is interesting. We're going to carry on with that calculation later on in the follow-up paper. However, you should immediately complain, and I'll be done in 2 or 3 minutes, folks, just in case you're worried about the time. However, you should immediately complain, which is the behavior of this ground state energy here. This is just a cartoon. I haven't calculated, or we haven't calculated this. And the reason is this is not reliably calculated from the IR theory. And that's because we don't know the form of the UV moduli stabilization in this theory. We don't know what dynamics sets the M Higgs mass square parameter. All right. So we don't know its contribution to the vacuum energy. So what I've done here is I've drawn it so it's always positive. And if it's always positive, because I know reliably the splitting to the extent states, I know these states are deeply in the region that is forbidden by transplanting censorship. And incidentally, also the swampland de Sitter conjecture as well. Okay. Well, you can complain. So what's really going on? Why have I done this particular thing about this ground state curve? So in particular, why couldn't the ground state curve go to deep ADS, right? And therefore, the excited states, why can't I move all this down and put this state, say, low down, and put this excited state very near zero and satisfy, let's say, the transplanting censorship conjecture? So that comes down to another recent conjecture, which is the de Sitter and anti-de Sitter distance conjectures. So this is in a paper of Luce, Peltier, and Baffer in 2019. And the statement here is there exists an infinite tower of states with mass scale m, which as the cosmological constant, this is in Planck units, goes to zero, the mass of this infinite tower of states goes to zero. Right? And this applies not only for anti-de Sitter, where there's a reasonable amount of evidence, but they believe also for de Sitter. So they say later on, and I'm with using this conjecture as part of our thing, at least for this transplanting censorship. So in this picture, we therefore have three branches, ADS, Minkowski, and de Sitter space, which is separated by infinite distance and metric space. This would suggest there's no effective field theory with a finite number of fields which can have families of vacua interpolating from one branch to the other. And in fact, they assemble, and there's been later evidence as well, there's evidence that in a given EFT, and remember, we're always assuming EFT is just the standard model low energies, the potential cannot cross zero vacuum energy in a smooth way. So if it can't cross zero vacuum energy in a smooth way, I mean, and let's say you know, we are just above zero over here at slightly negative Higgs mass square parameter, and then it varies over this range. A whole region where I just have the standard model and no infinite tower of other light of states becoming massless, then everywhere there's potential, it has to, whatever it is, whatever it's doing, it's above zero. And once it's above zero, then these excited states are well above zero because this splitting is reliably calculated. Okay, so that forbids this whole region. It's this set. It's not just a single conjecture that's doing it. It's the interconnection between different conjectures. So here's our strongest claims before I finish about the whole Higgs mass square parameter. So this is, I've explained this part of the space. In fact, you can make arguments that similar phenomena goes on for negative Higgs mass parameter. That's true if pure SU3 gauge theory has metastable states, like SUN in the large N limit has metastable states. If that's true, then this whole region from minus 30 TeV squared up to minus M Planck squared could also be forbidden. And again, emphasize, and of course this is on a log scale, the standard model sits and is okay in this narrow little window. So that's it. There's hugely more to say, but I don't have time here. So I'll leave you for that to leave that for you to read in our upcoming papers. So thank you. Thanks for your attention.
Thank you very much, John. Actually, there's a few questions in the chat room. John, can you see it?
Let me just turn it on. Let me see. No, why can't I see the chat? That's unusual. Usually I can see the chat.
Yeah, it's in the bottom.
Maybe I should stop.
Or maybe I.
Yeah, why don't? Oh, here it is. Sorry. Oh, it's differently. John, do you have an intuition as to why? So Jacob McNamara asks, John, do you have an intuition as to why the transplanting censorship can rule out points with a global symmetry? Only a roundabout way, which is if I have a Hart's global symmetry, then I can generate rather large. I can either generate indeed rather flat regions of the potential around that area, or I can generate these degenerate metastable states. And if I have, or degenerate states, and if I have degenerate states, right, even if I then split them ever so slightly, then the tunneling lifetime becomes incredibly long. So I immediately violate the censorship conjecture. So it's true, I mean, the degenerate state case, if they were exactly degenerate and both at zero, then I wouldn't. But if I have exponentially small splitting from that, then I raise one relative to the other, and the lifetime of that higher one is incredibly long. But I don't. I think it's a very interesting thing. It's very interesting to us that we found that it was global symmetry. It was always the global and enhanced points that were forbidden, and these extra things we were finding always cut out bigger regions around those points. So, I think. So, second question, John, large number D which appeared in your earlier computations, is this large by virtue of a parameter? Yes, it's because of various factors of pi and the like, exactly, and doing exactly what the bubble wall profile looks like.
Thank you.
So you can estimate it by counting pi's, and it turns out to be about a few times 10 to the 3. In fact, an accurate calculation finds it is even a factor of about 10 larger.
Okay, is there any questions in the audience? You can just raise your hand.
Yes, please. Obviously, I'm being, you know, we're taking as truth these conjectures, and of course we do not know these conjectures are true, or maybe they're slightly incorrectly formulated, or maybe they're subtleties in application in some case. Now, at the moment, I'm taking them to be correct and combining. I emphasize I'm combining at least two of them, right, to get these constraints, right? So I'm combining, for instance, the distance conjectures with Transplant censorship, or I'm combining some various other things. So if I do that, but then I find this remarkable thing that I can really start bounding the hypothesis. It's just the standard model. If just the standard model is purely the Lorentz effective theory, then I can start bounding the parameters using those two conjectures together.
John, I have a question. If you remove Transplant censorship as an assumption and just use the distance conjecture alone, or
Yes.
maybe distance conjecture and the de Sitter conjecture, but not Transplant censorship, is there anything that can be said, or does all of this go away?
Yes, you can still say certain things. There are definitely things you can say. You can't forbid the entire regions. It depends how much you want to do. So I'm giving you a picture that would allow us to forbid both to the far left and to the far right of 0, and also do the cases where you start moving ring couplings. But there are, if you start weakening the conjectures, you still forbid some parts of parameter space, but some parts are allowed. Yeah. So most certainly. And in fact, I think, of course, we've only made one set of arguments. So I think it's possible that there are other ways of making arguments. And in fact, my expectation would be, in fact, I should say, maybe this is what Rudin might, I think I hear Rudin. In fact, the thing I presented is the leading order analysis. I mean, something that Rudin has always been emphasizing to me. We're only here doing a leading order analysis. It wouldn't be at all surprising if higher order effects further split things and gave you a further spectrum of metastable states. And in fact, that could lead to a lot larger excluded range of parameter space. We haven't done that yet at all yet. Right, so, Rudin, was that your thing? You were about
well, yeah. Let me also say I agree with what you just said. For example, if you, I mean, we have toyed with including, say, the eta prime in the Cairo-Lagrangian calculations, and that just makes metastable states more likely. So I agree with that. And then in other situations, but also just to address Grant's question specifically, I think Grant, you asked what would be the situation if we exchange the Transplant censorship conjecture with the de Sitter conjecture.
That's right. Yeah.
Yeah, I just wanted to say, well, actually, the Transplant censorship conjecture is the weaker of the two. So actually, all this the exclusion becomes easier if you take the de Sitter conjecture.
Yes.
Yeah. I think what would be tougher would be to just use the distance conjecture.
Yeah.
Of course, the distance conjecture is currently the one with arguably the most evidence from string theory. But right, yeah, okay, that makes sense. Thanks.
Yes. Other questions, please. Any other things, folks? If not, I'm happy to. Well, can I just make one remark? So I said it very quickly. Do you mind if I go back to this? Can I just show you this one slide here? It is a remarkable fact. So if you take the Higgs mass square parameter to be very large and negative, right, then Higgs Bev is very large. And once it's above, once the Higgs mass square parameter is more negative than minus 30 TV squared, in fact, there's no light quarks. So the low energy theory now is pure SU3 Yang-Mills, right, for QCD. It's a remarkable fact, again, known for many years, that a large N analysis of pure SUN theories gives you a very rich spectrum of metastable states, even at theta bar equals 0. So it's really quite extraordinary. Now, this is not known, I should emphasize, this is not known whether it's still true for SU3 pure SU3. The large analysis breaks down, other semi-classical analysis break down. So it would be fantastic if somebody would do a lattice study of this situation and find out whether pure SU3 really does have metastable states. And also, it's important how long-lived they are as well, which is a more delicate question. Mike Tepper said at Oxford, said he might do this, but in fact, I think, this will be a really interesting calculation for some part of the lattice community to do. I mean, it would be quite fascinating. So if that was true, then we also forbid this pink region here to the left of on this figure.
Sorry, just one question related to this plot. So in this plot, you're allowing yourself to vary the Higgs mass square by keeping the Yukawa couplings fixed.
I keep the Yukawa couplings fixed, absolutely. But unless at least on the unless I put the Yukawa couplings at global symmetry enhanced points, which I claim is forbidden for other reasons, or I make them exponentially small. So notice the splitting here between this black line in the right-hand part of this plot here goes like y squared lambda QT6. So if obviously I sent the Yukawa couplings very exponentially tiny, then the splitting becomes so tiny, then in fact the Transplantian censorship at least doesn't forbid it. It could be the swampland conjecture still does, but Transplantian censorship doesn't. But almost all, my point is, or our point is, almost over all of your power coupling space, it doesn't matter what your Yukawa ratios are. The Yukawa space. The only special places when you have a global symmetry enhanced point, or where all y's are going to exponentially small values, which of course is sort of getting very close to another global symmetry enhanced point as well. Right? So.
Sorry, may I ask a question, John?
Yes, please, absolutely, I think. Good to see you.
So isn't that secretly an argument against the landscape as we know it, or as we think we know it from string theory? Because in the landscape, I would expect indeed that some small change would allow me to lift, in fact, our minimum. I don't even need your extra minima by a little bit.
Yeah, I think it is an argument.
And hence violate the conjectures.
I think it is an argument.
So I feel that somehow, if that is true and the conjectures are true, the logic just speaks against what we know as the string landscape of model building.
Well, I disagree about that. It gives trouble for the landscape at exactly 0 cc and positive, strictly positive cc. It allows a landscape in ADS.
No, I understand logically, but technically, it is hard for me to see where in the landscape as we know it, the conspiracy would come from, which would allow me to lower the energy of Bayer's minima a little bit and not to raise them. I would then rather say that the conjectures are so strong that this landscape simply doesn't exist. I mean, the other option is of course possible logically, but I just find it very hard to see that technical relation between raising or lowering some coupling and hence the minima. I
somewhat disagree about that logically. It could be that as you're getting, let's imagine we're starting to approach things from the antecedent direction. So we have some stable non-supersymmetric state, right? Of course, we care about whether this is stable or not. So it could be as you're approaching 0. Remember, there's supposed to be this infinite tower of Tates that is going down. So your effective theory is breaking down. It could be that once you get to 0, in fact, you never find the stable situation. Yeah, so it'd be perfectly okay if you just had, local saddle points or local maxima. So I claim the picture would be that you have a really a dramatic change in the character of critical points as you're going through 0. But the claim of Affer and co-workers is you can't study this in any given effective theory. You have to. The effective theories always have different branches, right?
Well, I understand, but I would call, to use your word, I would call that correlation mysterious, given my present understanding.
Yeah, I agree about that. Incidentally, it's obvious from these things, it should be obvious that here we're making a strong connection between the cosmological constant problem and the electric hierarchy problem, and maybe even other things, the flavor problems as well. We're saying that these are very deeply connected with the cosmological constant problem, which is striking. Of course, other people have conjectured such things in the past, but I think this is,
Okay,
at the moment, we're taking things, we're making the conjectures as true as stated and seeing what consequences we can withdraw. Right? So I think that's our approach, Arthur.
Okay,
thank you.
Yeah, if there's any questions, then we can continue. There's also a stack space where people can post questions and we can further discuss there.
All right, great.
So
Thank you.
let's
Thank
all
you very much.
thanks for a wonderful talk.